Good day everyone, and welcome to our presentation. We are Wei Kiat Chan, Pengwei Wang and Ray Chen, Hua Yao, and we're excited to share our research titled Creation of Novel Soft Robot Designs Using Generative AI. Our work delves into the fascinating intersection of AI and robotics, exploring how a diffusion model can revolutionize the design process of soft robots. Stay tuned as we unravel the potential of this approach and its implications for the future of robotics. In this slide, we'll delve into the key highlights of our research. Our primary motivation was to evaluate the effectiveness of a diffusion model for text-to-shape generation. We were particularly interested in understanding how the model responds to different numbers of folds in the shapes. We also wanted to assess how resolution impacts the model's performance. We addressed a couple of significant problems in our research. We noticed that existing models often lack detail when generating shapes. This lack of detail can be attributed to the complexity of the shapes and the limited resolution that hinders the model's performance. In essence, our research is a deep dive into the world of diffusion models, their capabilities, and their limitations. We believe that our findings will contribute significantly to the field and pave the way for future research. In this slide, we'll delve into the key highlights of our research. Our key insight is that transfer learning significantly boosts the performance of our model. Additionally, having a larger dataset helps the model to better understand the intricate relationships between different parameters. Moving on to our methodology, we utilized a diffusion model to generate 100 lines of text prompts. We then assessed the model's understanding of these prompts through a qualitative comparison and by examining the results of the generations. We also explored how the model responded to different numbers of folds. These findings underscore the potential of our approach, while also highlighting areas for future improvement. As we continue to refine our model, we anticipate even more promising results. Stay tuned as we delve deeper into these findings in the following slides. Moving on to the key highlights of our study. Our results showed that direct training was not as effective as we had hoped. However, we saw a significant improvement when we applied transfer learning techniques. When we tested our models with text prompts, the final model outperformed the others. For the first prompt, it was the only one to produce the correct generation. For the second prompt, while 3 models came close, the final model was the most accurate. These results underscore the potential of our approach, but also highlight areas for improvement. For instance, all models lacked important details, likely due to resolution limitations. In conclusion, our study demonstrates the power of transfer learning in improving mesh and surface quality. However, we also identified the need for larger datasets and better GPU performance to overcome resolution constraints. Remember, these are just the key highlights. There's a lot more to our study, and we're excited to share the details with you. Stay tuned. Moving on to the key highlights of our study. Our current approach has a few compromises. Firstly, we are dealing with a small resolution, which is a constraint imposed by the GPU performance. This means that the quality of our results is limited by the computational power we have at hand. Secondly, our generation process is solely focused on shape, without considering physics or materials. This is an area we aim to improve in future work. Despite these compromises, we believe that scaling up our approach should significantly improve the results. By increasing the resolution and incorporating more parameters into our model, we can generate more accurate and detailed designs. Stay tuned as we delve deeper into our future plans in the next slide. Let's dive into the heart of our research. Our primary goal was to evaluate the effectiveness of a diffusion model for text-to-shape generation. We wanted to understand how this model responds to different numbers of folds, and how resolution impacts its performance. Take a look at this figure on the screen. It illustrates how our text-to-shape generation model responds to different numbers of folds. You can see how the model's understanding of the description changes with data augmentation. It also shows the impact of target resolution on detail preservation in long actuators. In essence, we're exploring how we can use AI to generate soft robot designs. We're pushing the boundaries of what's possible, but we're also aware of the challenges we face, such as GPU performance and dataset size. But as researchers, we thrive on these challenges, and we're excited about the potential of our work. Let's take a closer look at the problem we're addressing and its significance. As you can see in this illustration, we're exploring how our text-to-shape generation model responds to different numbers of folds. This demonstrates the model's understanding of the description with data augmentation and the impact of target resolution on detail preservation in long actuators. Now, why is this important? Well, the implications for the design and optimization of soft robotic systems are vast. We need diverse and high-quality designs to push the boundaries of what's possible in this field. This research is a stepping stone towards achieving that goal. We're not just creating designs, we're teaching a model to understand and generate them, which opens up a world of possibilities for innovation and advancement in soft robotics. Let's now delve into the limitations of previous approaches. One of the key challenges we faced was the resolution limitations. This led to a lack of important details in the shapes generated by our model. As you can see in the figure, the model's understanding of the description with data augmentation is demonstrated. However, the impact of target resolution on detail preservation in long actuators is evident. Furthermore, as the complexity of the model increased, we noticed a decrease in the visibility of details. This is a significant hurdle, as it limits the model's ability to generate intricate and detailed designs. In the next part of our presentation, we will discuss how we address these limitations and the innovative solutions we implemented. Stay tuned. On this slide, we delve into our proposed approach. We've utilized a diffusion model to generate soft robot designs. To evaluate its effectiveness, we generated 100 lines of text prompts, mirroring those found in our training dataset. We then assessed the model's understanding of these prompts through a qualitative comparison and by examining the generated results. As you can see in the figure, it illustrates how our model responds to different numbers of folds. It demonstrates the model's understanding of the description with data augmentation and the impact of target resolution on detail preservation in long actuators. This approach has allowed us to explore the potential of AI in generating novel and functional soft robot designs. However, it's important to note that our results are not without limitations, and there's still much to learn and improve upon. As we delve deeper into our research, let's take a look at this illustration. It showcases how our text-to-shape generation model responds to varying numbers of folds. You can see how the model's understanding of the description is enhanced with data augmentation, and how the target resolution impacts the preservation of details in long actuators. Now, let's highlight some unique aspects of our approach. Firstly, we've investigated the model's response to different numbers of folds. This has provided us with valuable insights into the model's adaptability and flexibility. Secondly, we've utilized transfer learning to significantly improve the model's performance. This has proven to be a game changer in enhancing the model's ability to generate more accurate and complete shapes. Lastly, we propose to scale up the model and use a larger dataset. This will not only improve the model's understanding of parameter relations, but also its overall performance. In essence, our approach is a blend of innovative techniques and strategic improvements, all aimed at pushing the boundaries of what's possible in the realm of soft robot design generation. In this slide, we delve into the related works in the field of soft robotic systems. We will explore the various approaches that have been undertaken to design and optimize these systems. This includes a deep dive into the different diffusion models used for three-dimensional shape generation. These models play a crucial role in the design of soft robots, providing a foundation for their structure and functionality. We'll also discuss how these models have been applied in the design process, shedding light on their practical implications. This exploration of related works will give us a comprehensive understanding of the current landscape in soft robotic systems design and optimization. In our exploration of generative AI, we've seen the impressive performance of diffusion probabilistic models, or DPMs, in image generation tasks. They've truly set a new standard in this field. Now, let's compare diffusion models with other popular models like generative adversarial networks and variational autoencoders. What sets diffusion models apart is their stability during training and the superior quality of the samples they generate. Unlike GANs and VAEs, diffusion models don't require explicit latent variable sampling during training. This makes the training process more efficient and the results more reliable. In the next slide, we'll delve deeper into the unique features and capabilities of 3D diffusion models in the context of soft robot design. Stay tuned. In our exploration of related works, we've seen the significant role that diffusion models play in the realm of soft robotics. These models are instrumental in capturing long-range dependencies, which are crucial for generating complex soft robot designs. These designs exhibit intricate structures and functionalities that are key to their performance. Moreover, diffusion models are essential in estimating uncertainty. This is particularly important in soft robotics applications, where designs must be robust to variations in material properties and environmental conditions. By incorporating these models, we can create designs that are not only innovative, but also reliable and adaptable to a variety of scenarios. In the next part of our presentation, we'll delve deeper into how these models are applied in practice, particularly in the design of soft robots. Stay tuned for some fascinating insights. In our exploration of related works, we've come across several intriguing 3D diffusion models that have been proposed for soft robot design. Models such as Text-to-Shape, S-Diffusion, DreamFusion, and Point each bring unique features and capabilities to the table. For instance, Text-to-Shape leverages text descriptions to generate 3D shapes. Imagine the possibilities this opens up for creating 3D shapes based on textual specifications. On the other hand, S-Diffusion focuses on generating shapes represented by sign distance functions, which allows for the creation of complex, multi-part designs. These models, with their diverse approaches, are truly revolutionizing the field of soft robot design. They are not just creating shapes, they are shaping the future of robotics. Stay tuned as we delve deeper into these fascinating models and their applications. In our exploration of soft robot design generation, we've found two key factors to be of utmost importance. Firstly, transfer learning. This technique has proven crucial in achieving better mesh and surface quality. It also aids in understanding the interrelations of different parameters, enhancing the model's overall performance. Secondly, the size of the dataset. A larger dataset not only improves the model's understanding, but also contributes to better generation results. However, our current approach does have its compromises. The resolution is small, primarily due to GPU performance constraints. This limitation affects the level of detail in our generated designs. Furthermore, our generation process currently only considers shape. It doesn't take into account physics and materials, which are vital aspects of any real-world design. Despite these compromises, we believe that our approach holds promise, and that improvements can be made by scaling up and incorporating additional factors into our model. In this slide, we delve deeper into the technical aspects of our research. We've used a diffusion model for our text-to-shape generation. This model was evaluated based on its understanding of prompts, its ability to respond to different numbers of folds, and its performance in terms of shape completeness and surface quality. The figure you see here showcases the qualitative results of our text-to-shape generation. It clearly illustrates the significant enhancement in surface quality and shape when we apply transfer learning. Additionally, data augmentation has proven to be beneficial in improving the model's understanding of the shape. In essence, our approach leverages the power of diffusion models, transfer learning, and data augmentation to generate 3D shapes from text prompts. This innovative method has shown promising results, as you can see from the figure. We believe that this approach can open up new possibilities in the field of 3D modeling and beyond. On this slide, we delve into the technical details of our research. As you can see in the figure, we present qualitative results of text-to-shape generation. The comparison is made between models with and without the application of transfer learning and data augmentation. The figure clearly illustrates the significant enhancement in surface quality and shape understanding brought about by transfer learning and data augmentation. Now, let's talk about the problem we're addressing. Our aim is to understand the model's ability to generate shapes based on text prompts. We're particularly interested in how the resolution impacts the model's performance. As we increase the complexity of the model, the limitations in resolution become more apparent, affecting the model's ability to capture finer details. This is a key area of focus for our research. In the next slides, we will discuss our proposed solutions to these challenges and the future direction of our work. Stay tuned. On this slide, we delve into the technical details of our proposed solution. We've employed a diffusion model and generated 100 lines of text prompts, similar to those in our training dataset. This approach allows us to compare the effectiveness of direct training and transfer learning methods. As you can see in the figure, the qualitative results of text-to-shape generation with and without transfer learning and data augmentation are displayed. It's clear that transfer learning significantly enhances the surface quality and shape, while data augmentation improves the understanding of the shape. We've evaluated our final model based on its ability to generate the correct shapes from the prompts. This evaluation process is crucial in understanding the strengths and weaknesses of our model, and in identifying areas for future improvement. In essence, our proposed solution is a testament to the power of transfer learning and data augmentation in the field of generative AI. On this slide, we delve deeper into the technical details of our research. We have a figure here that visually represents the qualitative results of our text-to-shape generation. It clearly shows how transfer learning and data augmentation can significantly enhance the surface quality and shape understanding. Our experiment design was quite comprehensive. We created a dataset consisting of 100 lines of text prompts, similar to those used during training. The evaluation criteria were based on the model's understanding of these prompts, the completeness of the shape generated, and the surface quality metric. We also tested the model's ability to respond to different numbers of folds. This was a crucial aspect as it allowed us to assess the model's adaptability to varying complexities. In essence, our research is a blend of rigorous experiment design and innovative application of AI techniques, all aimed at improving the generation of soft robot designs. Let's delve into the technical details of our research. As you can see in this figure, we've compared the results of text-to-shape generation with and without transfer learning and data augmentation. The results are quite telling. When we used direct training, the results were not up to par. However, when we incorporated transfer learning, we saw a significant improvement in the quality of the shapes generated. We tested our models with 2 prompts. For the first one, only our final model was able to generate the correct shape. For the second prompt, 3 of our models came close. But again, the final model was the most accurate. However, as we increased the complexity of the model, we started to lose some details. This is due to limitations in total resolution. In summary, our technical results show that transfer learning can significantly enhance the surface quality and shape, while data augmentation can improve the understanding of the shape. However, we need to address the resolution limitations as we increase the complexity of the model. Let's delve into the key results of our study. We found that direct training of the diffusion model didn't quite hit the mark, with the poorest results in terms of shape completeness and surface quality. However, we saw a significant leap in performance when we introduced transfer learning, underscoring its vital role in achieving better mesh and surface quality. Now, let's consider how the models responded to text prompts. For the first prompt, only the final model was able to accurately generate the correct shape. For the second prompt, 3 models came close, but again, the final model outperformed the rest. As we increased the complexity of the model, we noticed a trade-off. While the models could handle different numbers of folds in some cases, the visibility of details decreased due to limitations in total resolution. Take a look at the figure on the screen. It showcases the qualitative results of text-to-shape generation, demonstrating the impact of transfer learning and data augmentation on surface quality and shape understanding. This is a testament to the potential of our approach, despite the challenges we faced. In conclusion, our approach utilized a diffusion model for text-to-shape generation. We focused on the model's ability to respond to different numbers of folds, which was a key parameter in our dataset of soft pneumatic robot actuator designs. We also examined the impact of resolution on the model's performance. We found that while the model was able to generate accurate shapes, the level of detail was limited by the resolution, which is constrained by GPU performance. Despite these limitations, our results showed that transfer learning significantly improved the model's performance, particularly in terms of mesh and surface quality. However, there is still room for improvement. For instance, the model currently only considers shape and does not take into account physics and materials. In the future, we believe that scaling up and using a larger dataset could significantly improve the results. Thank you. In conclusion, let's highlight some key aspects of our approach. We generated 100 lines of text prompts, mirroring those in our training dataset. This allowed us to assess our model's understanding of these prompts. We conducted a qualitative comparison and generated results from each model to evaluate their performance. Our evaluation was based on 2 main factors: shape completeness and surface quality. These metrics gave us a comprehensive understanding of how well our model was performing. It's important to note that while our results are promising, they are not without limitations. However, we believe that these challenges present exciting opportunities for future research and development in this field. Thank you for your attention.